My name is Jeremy Lebon. I'm a lecturer and a researcher at the University College in Belgium, in Kortrijk. I will present you one of our currently running projects, the remote control of a skid steer. But first of all, I want to introduce our University College. It will be very short. Vives University College is located in Belgium, more precisely in West Flanders. And there on the left you can see that I am currently working at the campus in Kortrijk. We are also a member of the KU Leuven University Group. We are a university college. That means that we have bachelor degree students who study at our university college. There I teach primarily vehicle electronics courses, but most of my work is in our research group in vehicle networks, where we give training around different kind of communication systems. Primarily is it CAN bus, J1939, iSBus, LIN bus, CAN open, now also FlexRay, and also training over mobile automation, where the communication meets the application, who has to be controlled. Second part of our research group is the research itself. You can see below that's a small scale sprayer setup where we want to, where iSBus is integrated. Now it's completely programmed by ourselves, but this year it will be updated to the right kind of standard of iSBus. We also give consultancy to companies, local companies in Belgium, primarily when or how to implement CAN bus on a specific machine. So this is a short introduction of our research group. So back to the focus of the presentation. This is the agenda of my presentation. First of all, the short introduction around the project, the objectives of the project, a machine overview, network overview, different used components, and then also the future, because this project isn't over, it's still running. This year we will enhance the machine. So this is a short introduction. In Belgium there are still approximately 300 tons of bombs found every year. So that's a lot of bombs. These has to be excavated from the ground, and to do so on a safe manner, the Belgian army has given us the task to convert a mechanical skid steer. So they have 16 of these skid steers, really old ones, I think 1979. So we have to convert them so that they can be controlled remotely, so that the bombs can be excavated on a safe manner without any hazard of explosion. This project is primarily executed by our bachelor students under the guidance of our research group. So in 2015, the first the project started with a study of feasibility of is it possible to convert these mechanical skid steers to be remotely controlled. The previous year, so 2016, all the different things that had to be modified, so electrical, hydraulically, the CAN bus, the communication between everything has been implemented, so it's a very nice project. Okay. So the objectives were, 2016, of the start of the project, was to modify a mechanical controlled skid steer. So you have your mechanical joysticks. There weren't any CAN buses present in the machine, so it was really basic machine. We have to make hydraulical changes, electrical changes, mechanical modifications, and also the integration of not one network, but 4 different CAN networks that have been implemented. So that were the objectives of the project. There also the cabin of the skid steer had to be reinforced, because when there was a bomb blast, the electronics inside of the machine had to be protected. And so if the machine exploded, electronics could be taken out, put in a new one, or in another one, and used for, again, for excavating bombs. So you can see later on in the mechanical modification, everything is built so that if it's broken, if it explodes, all the electronics can be built out for other skid steers, or for another skid steer. So these are the modification. This is the machine overview. These are all components. Most of the components are added to the machine to make remote control possible. You can see on the left-hand side the inputs. We have our remote control, a cleaner sensor, our safety control, so the brain of the machine. Visualization with a little display. This will be altered this year to a bigger screen. And then the outputs. So we have the horn, lights, hydraulic actuators are one of the important components in the machine. Gas throttle actuator, and then components like starter, diesel pump, and traction lock to make the machine moving. This is a basic necessity. So that was the machine overview. The network overview, you can see we have our safety controller with 4 different CAN networks. We have a CAN open network, 2 CAN layer 2 networks, so that's specific by our specification, so we use it like we want to. And then the third one, CAN 3, is a J1939 actuator to control a gas throttle actuator. CAN open, our master of our controller is the CAN open master. We have 2 CAN open slaves, so one for the remote module. So we have a sender and a transmitter. The sender transmits over Bluetooth to the receiver. Receiver converts information to CAN open messages, and these CAN open messages are received by our safety controller. Also, a cleaner sensor is a CAN open sensor who delivers information of the inclination of our machine. Because one of the objectives was to control the machine over a length of 200 meters, so then it's not really possible to see how inclined the machine is. That's why it's built in. It is also so that the remote control will not be wireless, because in the field where it can be used, for example, road clearance, where they want to clear roads from bombs, mostly the frequency of Bluetooth and other communication frequencies are jammed, so it will be wired. So we have to use a CAN cable to control the skid steer. So this is the CAN open network. Second network is the J1939 network, so the basic network that's been used for communication between engine and transmission and etc. Here it's used to command a gas throttle actuator by specific messages. You will see the messages in one of the following slides. So this is our J1939 network. Then 2 proprietary CAN networks, one to program our controller, our safety controller, and one to display information of our skid steer. So that's the topology of the CAN network. Now the components, so we have one safety controller, 4 CAN buses on the safety controller. You will see it in one of the following slides. To control the hydraulic actuators, we have specific outputs. We need specific outputs, the PWME, so the current control outputs to control the hydraulic actuators. And we have other outputs to, for example, control the horn when necessary. So this is a safety controller, so the brain of our controller. Also the gateway between the different kind of CAN communications, because with our with the remote control, there are a couple of buttons to adjust the gas throttle. This information is sent by CAN open, is converted to information so that we can control our gas throttle actuator. So that's a kind of gateway. Also remote control, so a lot of joysticks, or 4 joysticks, XY joysticks, a lot of switches, toggles, emergency switch. There are also switches on the left side and the right side to start the machine, to stop the machine, to change the RPM of the skid steer. So all this information is put in 2 transmit PDOs that are sent to our safety controller and that are used for controlling our outputs. So that's the schematic of one of the graphs of the joystick. So that's the information that can be seen on the CAN analyzer. Same inclino sensor, also safety, also CAN open node or module. The information has been sent to the safety controller, and the safety controller puts the information on CAN 2 of our system so that we can see the actual inclination of our machine on the display. It is also so if inclination is above 75 degrees, the machine stops automatically. So it's programmed in our safety control that this can be done. So these are the 2 CAN open slaves. Then the gas throttle actuator, so it's controlled with J1939. And you can see there are 2 messages. One message to command the actuator. So with one parameter, with one value, we can put a value in so that the stroke of the actuator changes accordingly to the data put in the value. So that's one message. We can command the actuator, and we get one feedback message who says what's the stroke of the actuator. There are also 2 other messages, but they are not on it, but purely for the diagnosis of the actuator throttle. There's the gas throttle. Then the display, so all important stuff of the machine are visualized on this display. You can see the RPM of the skid steer. You can see the information of the inclino sensor. You can see all the different parameters of are the lights on, is the horn on, and so on. So this is our display. Programming is done in EAC 6131 environment. Our students also get this as a basic programming language, and in the 3rd year, in the year where they make their thesis, they have used this environment to program the skid steer. So it's a structured text, a little bit like the Pascal programming language. So this is the programming. This will be changed this year Also because we have to change to another controller because we have a limited amount of I/O if we want to do the things that we want to do this year. So this is the programming. Mechanics, you can see we have there's built-in bracket, and on the bracket you have the different kind of actuators. There are 4 actuators for the 4 different movements, for driving, for tilting. So there are 4 different actuators. These brackets are built so that if the machine should explode, bracket can be taken out and put in a new, of course the same type skid steer, but you can reuse it. Also, there is a build. The cabin has been reinforced for above. It is also not possible to take place in the machine. There isn't any space anymore. So this is the mechanics. Hydraulics, very interesting actuator. It's controlled current control. So there are 2 valves on the actuator. And we can control the stroke with a current value. The stroke of the actuator is only 13 millimeters forward and then 30 millimeters afterwards or backwards. So it's not a lot, but it's sufficient for controlling our skid steer. So every movement can be done with this actuator. The main advantage of this actuator is when current is interrupted, they go to a safe state. So they go to a safe state, and then the machine can't move anymore. He will stop automatically, because we have looked for other options, but this one is the safest. So that's the hydraulic actuator. Future, that's for this year. Normally they will start in March. There will be adjustments, so there will be a new controller, because we want to control other movements with hydraulic actuators, and the safety controller hasn't enough specific outputs for this controlling. Further on, there will be additions to this counterbalance, because the machine has a very large shovel. I don't think if you saw it. So, below you can see it's a very long shovel, and the machine isn't in balance, so there will be placed a counterbalance weight. Also, because we want to remote control the machine, we should have cameras. This year they will be placed on the machine, so different kind of cameras. Also, the Belgian Army has asked us to make an auto-diagnose system for the machine, and therefore extra pressure sensors and speed sensors had to be added to the machine. So this is what we want to do this year, and then future and dreams is to add a 3D camera so that he can see obstructions in the field, and even more, and also adding GPS RTK tracking and guidance system to automatically driving. Because, for example, you mark a spot, here's a bomb, and the machine will drive automatically to that location. So thank you for your attention. Any questions?
Yeah, thank you, Mr. Lebon. I'm sorry that you have so much bombs from the Second World War. Yeah. I feel a little bit guilty, because my father was, when he was 16, fighting in Belgium. He was still a boy, but please excuse that you have so much trouble now with these bombs. Yeah, are there questions? Christian?
Yeah, hi. One question. You showed that you have several proprietary networks. But what we could see is that it's only a point-to-point connection. So why don't you have put all the proprietary nodes on one network?
Because we had CAN networks over, so we had the possibility to do so. It can be that in the future there will be only one proprietary CAN bus and, for example, another one for Isobus or something like that. It can be.
And I saw that you also have some plans to extend the communication in these machine, and maybe you're looking still for sponsors, and I think the companies are invited to sponsor you by means of products or tools or whatever you need. Okay.
Yes,
Thank you.
That's one of the points that we came here for.
Yeah, I can imagine that. Are there more questions?
It's not CAN related. You said there are still 300 bombs a year they found. Are there still bombs from World War I?
I think so, yes.
Oh.
Are there other questions? If no, then thank you
Yep,
again.
thank you.